So the project I'm going to discuss today is how to draw and map terrains, and along with the texture mapping from a third-person shooter perspective. And if possible, we will also be adding some characters and some motion and animation to the terrain. Why do we need to draw terrains? Firstly, we can draw terrains to obtain realistic maps of places that we would like to visit or places that we'd like to explore. We can travel through these maps, and as most of you know, games depend entirely on maps. We can also simulate hostile places or inaccessible places in terms of a terrain, and then just traverse through it to know what obstacles we could face and which particular obstacle actually exists in which particular place. The top level steps in actually drawing a terrain include firstly loading the terrain map, applying the texture map. The texture determines what color the terrain is going to be and how the ground is going to look, whether it'll have grass or whatever it is you want to put on the terrain. And finally, we position the camera the way we want it. Of course, in addition to this, you may want to have the ability to move the camera around the terrain or add a character if you're making a game or a simulation or things like that. Now, loading the terrain map. The first step in this is loading something called a height map. This height map helps us calculate the vertices of every point on the terrain, and finally we calculate the normals of every point. The height map is nothing but an image in the XZ plane, and it is something similar to the image shown on this slide, and the information that it holds is of course the X and Z coordinates, and for every point on the X and Z coordinates it holds a pixel which is either black or white or anything in between that's gray. And so every pixel holds the height in terms of y-axis at that point. Now these images could be raw or bitmap or JPEG or whatever it is that you desire, but most people prefer to use raw images since there's hardly any headers or compression and they're much easier to deal with. But for this example, we're going to be dealing with bitmap images because they're pretty easy to use, and you can open them and edit them in something as trivial as MS Paint. The main advantage of a height map is it gives you a nice idea of what the terrain is going to look like. For example, just by looking at this picture, you can imagine the terrain to be made up of something like a mountain here, because the white denotes the highest points, and these are slopes from the mountain all the way to this black area, which denotes the level land or the valley, whatever the case may be. Now, how do we load this height map into our program? We first obtain the height map as an image object, and then for every pixel we calculate the corresponding height. Now you could use any formula that you want to. I've used a pretty simple formula here. So for every pixel I essentially calculate the color and divide that by 255, since 255 is the maximum intensity that a pixel in an image could have, subtracted by zero point 0.5, and this sort of normalizes the entire y coordinate so that things are not too high or not too low, and they're pretty smooth. The height scale that I'm multiplying this entire equation with denotes how high you want the highest point to be and how low you want the lowest point to be. We now store these x, y, z coordinates in an array of vectors and compute the normal at each point. These arrays of points and normals essentially are our digital terrain. Now we come to the interesting part, the actual drawing of the terrain. We draw the terrains as triangular strips rather than polygons or any other geometric object. The reason for this is simple, because a plane is defined by a minimum of 3 points. More than 3 points could mean that some of the points are outside that plane. So if we take triangles and connect every 3 points, we're sure that this triangular plane is definitely going to be in one plane, and we won't have any jagged edges or any missed areas on the terrain. So we take the entire terrain and consider every row of the terrain as one strip of triangles and go through all the points in the terrain. Let's take a quick look at how this code actually appears. This main file is the file that pretty much does everything, and as is apparent, we have a class called terrain which defines our terrain object. It's got variables for width, length, arrays for heights and normals, and it's got a couple of interesting methods like this one right here, which computes the normals given the points of the terrain. It also has important getters and setters like get height and get width and set height. An interesting thing to note in this program is the WEG3F object. Now I got a couple of classes downloaded from the internet actually, and one of them is the WEG3F class. And it's a pretty beautiful class actually. What it does is it lets us define and operate on vectors. So as you can see, it's got an array of 3 elements, x, y, z, and it overloads a couple of operators, so you can multiply the vectors, divide the vectors, add, subtract, have direct access to these vectors. It's also got functions for magnitude and normalization and dot products and cross products, and all these things help us to basically find out normals and average the normals across a couple of points, just so that things are pretty smooth in our terrain. We now come to this first function in our main.cpp, and it's called load terrain. It takes in a file name and a height. Height is the scaling variable that I just talked about, and which determines how high or how low our highest and lowest points should be. We use another interesting function here called loadBMP, which again I downloaded from the internet, and this function takes in a file name and converts it. If everything goes well, it converts it to an image object and returns that right here. So once we have the image object, we go through every pixel in this image object and calculate the height based on the formula, and in the terrain we set height for that particular pixel to the height that we just calculated. And here of course we create an object of class terrain, calling it underscore terrain. The draw scene function is where we actually draw the terrain, and as you can see here, after a couple of scaling and translations just to make things look better, we have a pair of nested for loops which essentially go through the z and the x axis of the terrain. So for every z we find out every x, and for every pixel we plot the vertex as x, the height at that particular point, and z. And as we're using triangle strip within the first for loop, what this means is for the entire row we are making one triangle strip, and we go through each row by following z. And in our main function is where we actually load the terrain by calling load terrain function and passing this bitmap image and the height scaling factor. So let's take a quick look at how this actually appears to us. And there you go. This is how the terrain looks. As you can see, all the contours are pretty accurate, but the color is a bit odd. For some reason I selected the red color, and it looks like a nice little valley, and let's see if we can add some nice textures or better colors to this.